It's a pretty straightforward method, and it works all the time. Okay, now let's look at Newton-Raphson method. And secant method is very similar to Newton-Raphson. So I will describe both of them one by one. So this is my function, f of x. Okay, this function. Now the root is here. By the way, this is by Isaac Newton. Huh? So Newton is giving this method. The same great Newton. So we take a coordinate x naught, and value of the function at x naught is fx0. Okay. So at this point there is a slope. So get the slope f prime x, and slope will hit the x-axis at x1. Okay. So your x1 is a new point. So from this geometry, you can just see the geometry. Slope f prime x naught is fx0 y this divided by this. Okay, so fx0 divided by x0 minus x1. Okay, so from this we can solve what is x1. This is straightforward. X1 is x0 minus fx0 by f prime x0. Okay. Now, so that is my new x0 point, and okay. Now, what do I do next? I start from here. Now, compute the slope at x1, and I reach here. So that is going to be my x2. And now at x2, compute the slope. You can see that this is converging, right? I mean, this is going to converge, and in fact, convergence is better than bisection method. And okay, so Newton always has something creative, something very interesting. This is the first step, but in any nth step, which is you take xn and minus fxn minus divided by f prime xn. Okay, so given point xn, I can just get xn plus 1. Okay, that is xn plus 1. Now, for this particular example, it converges, no problem. But sometimes it doesn't converge. So I'm going to show you an example where it won't converge. So let's look at the error now. We can just do the error estimate. So we have this formula xn plus 1 equal to xn minus. So I just repeated the formula fxn divided by f prime xn. Subtract these both LHS and RHS from x star. So x star minus xn plus 1 x star minus xn. Okay. Okay. Now, so minus minus becomes plus. Now, I'm expanding both fxn and f prime xn by Taylor series around x star. Okay. So fxn is fx star minus x minus xn, which is epsilon n. Okay. Epsilon n is x star minus xn. Okay. And the second term and higher order terms. Now, bottom is f prime x star, like that. Now, what is fx star? This is 0, right? Because x star is the root of the function, 0. Now, so we get this is epsilon n minus, it is plus, but I'm going to take epsilon out from the top and divide by f prime both sides. So, well, both sides is up and down, numerator and denominator. So, this becomes 1 plus minus half epsilon squared f double prime divided by f prime, and ignore the higher order terms. And the bottom I will get f prime x, I divided already, so that becomes 1 minus epsilon n f prime f double prime divided by f prime. Okay. Now we do the Taylor expansion of the denominator. Okay. So this becomes epsilon n. By the left hand side is epsilon n plus 1 minus epsilon n. Now this is 1 minus half epsilon n squared, that object, f double prime by f prime, and this is becomes 1 minus f prime is here. Okay, we get here 1 minus x to the power minus 1, which is 1 plus x, which is 1 plus epsilon n f double prime f prime and higher order terms. Okay. Now we just do the expansion first. This will cancel with this, and you'll get from here. If you do all the algebra, we'll get this. Okay. So I'm just skipping the algebra, which is epsilon plus 1 is half epsilon n squared f double prime by f prime. Okay. So it comes from this factor. No, this epsilon not square. This epsilon. Okay. This epsilon, because epsilon, one epsilon is out. So you'll get basically leading order term will be coming from here, which is plus half, and the minus n here, so we'll get minus half. So you can see the error is decreasing quadratically. Epsilon n plus 1 is, so imagine the epsilon n is 0.1. So epsilon n plus 1 will be 0.01 squared. Well, I mean, there's prefactors, but then next time 10 power minus 3, then 10 power minus 6, and so on. So, sorry, this is 10 power minus 2, then 10 power minus 4. So it's quadratic. So it's a faster convergence. Okay. Now, this method fails on some occasions. One example is here. So if I start from x0, so here, I take the slope, which is, this plot is not extremely great, but here I come here. Okay. So my x1 is here. Now I compute the slope at this point, and I'm basically going away from the root. See, I'm going away from the root. Now this happens when this object, basically f prime is small. Okay, the slope is small. The slope is small, then f dot prime by f prime becomes quite large. So if this quantity is large, then my error is not going to decrease. Epsilon n plus 1 will be bigger than epsilon n. Okay, and so you have to watch out for this kind of scenarios. So bisection method, though it is slow, it is always going to converge. Newton-Raphson is good, great method, but it works only when this quantity is not large. So let's look at the same example. Again, I made a mistake. It's exponential x, and you can see that the solution is log x, log 6. It converges very quickly. For bisection method, it takes around 10 steps to get to accuracy of 0.001, and here it is in 5 steps. Okay, so this is indeed fast. I mean, it yields faster convergence. But for this problem, it doesn't converge. Here, it remains close to 0 for a while, but finally it just explodes. It just goes to, in fact, 10 power 29. This is the y-axis is too large. That's why it doesn't mean that it's close to 0. It is growing, and it just explodes. Okay, so this is not going to work for this problem.